Welcome to Pratidhwani, where we try to humanize science. It is my delight and pleasure to welcome the guest on this particular episode, Nirmal Raj. Nirmal is a theoretical physicist who also is very interested in collaborating with experimentalists, which is an interesting thing by itself. More importantly, he is an outstanding scientist who has been exploring various interesting questions related to dark matter, hunting dark matter, and trying to set up some particular viewpoints and also kind of theories and experiments related to detection of dark matter. Along with that, he has been communicating science. He writes at the Hindu and other kind of platforms. He is also on Twitter and is a fantastic science communicator. And it's my pleasure to introduce all of you, Nirmal. Nirmal, welcome to Pratidwani.
Thank you so much, Pavan. Thanks for the very kind and thorough introduction.
Yeah,
Very
my,
delighted.
my pleasure. Yeah, my pleasure. So, Nirmal, tell us about how you got interested in science and how you kind of developed into a very interesting kind of researcher, because the area of work what you explore is also not very conventional, because there is something which is very interesting about the way you go about doing your research, including the topics which we're going to expand later. But tell us a little bit about the foundations behind how you got
Okay.
interested in this.
The foundations. Okay.
Mm, mm.
Okay. How far back should I go? Maybe it is useful to separate science as science and science as a profession, research, etc.
Yeah, yeah,
Maybe I'll start
exactly.
with the
Yeah.
first one.
Yes, yes.
So, um, so I guess maybe in my fifth standard or so, that is when I started thinking I wanted to be a scientist. I didn't really know what that meant, but this
Mhm.
came about reading Jules Verne's books and things like that. And so I had some romantic notion of what it meant to be a scientist, some kind of a lab, uh,
Mm.
you know, things that robots that bring food to you, images from Chitty Chitty Bang Bang, and things like that. Basically, some very romantic notions. But really, I would say the real foundation of my passion for science
Mhm.
came came in eighth standard. That was a very clear point. This
Mhm.
happened entirely via a friend that I got. Uh, Her name is Neeta Chandrasekhar, and
Mm.
she was a puzzle enthusiast. I
Okay.
mean, she had a lot more passion for science and math and all that. And for some reason, she saw the same in me. And for whatever reason, she just wanted to be friends with me. And she just kept feeding puzzles and science facts and things like that with me, and just pumped me with this, with this whole world of, physics and chemistry and everything that I was not aware of before. So that was a very
Nice.
clear turnaround for me. Actually. That's the first time I saw that, oh, there's so much more to this than what you see in school. And there's a lot more calculations. Science, thinking of science as puzzles was something new to me.
Mm. Mm.
So in my memory, I always think of that as my entry point into my life in science. And I'm always grateful to her. I'm still in touch with her and all that. I'm always
Is she
grateful.
also a scientist, or
So today she is not a scientist. She's a scientist by heart. By
Yes, yes,
profession,
of course, yeah.
she's a hardware engineer. Oh,
Wonderful.
she works at Intel. She works at Intel in the USA. I think she's
Nice,
a chemical
nice,
engineer. Yeah,
nice. Okay,
yeah.
okay.
Um, so, but after that, it was very clear to me that if I was gonna make money, so I also wanted to be a writer on the one hand, but even back then it was sort of clear to me I was not gonna make much money in that. I didn't know anything about
Mm.
that market and all that, but I knew, some half of me knew that if I was going to actually have a sustainable life, why not science? Actually, I do like this, and I seem to be good at this. Why don't we pursue this? And I
Nice.
guess the next foundation came during my JEE preparations.
Mm.
Um, so, so like everybody else in India, I went for JEE coaching
Mm.
for IIT. I don't know what it is called these days, but for to get into IIT those days, you needed to write this joint entrance exam, IIT JEE.
Mm. Mm. Mm.
And there, I happened to get very good teachers in all subjects actually. So in Chennai, so I was
Mm.
born and raised in Chennai, and
Okay.
we went to a school called Satyamurthy for this coaching. And the teachers there transcended the coaching basically. In
Mm.
fact, some of them would explicitly tell us, if you don't get into JE, don't worry, but these are the treasures that you are carrying throughout your life, the things that you learn.
Very
So
nice. Very nice.
yeah, yeah. So I fancied myself to be an organic chemist actually. Until in my 12th standard, I got three superlative physics teachers. Um,
Mm.
Two from the coaching center and one was my school teacher, and that really changed everything. So it was all due to those teachers actually. There, I mean, I couldn't see the world outside of the physics lens after that.
Nice.
So it motivated me to study much harder actually, because now I really wanted to get into IIT Madras or IIT,
Mm.
and that way I could sustain, I could at least have a chance of following a career in physics. And
Nice.
I did get in. I got into engineering physics, um, and okay, so thus far I think I've spoken about science as science, but I was still not sure I wanted to do research and all that. I didn't have a very good clue of what that was.
Yeah. Before we
Yes, yes,
actually take
yes,
the plunge into the
yeah, yeah,
becoming a scientist part,
yeah,
there are two important aspects. One is while growing up, you are exposed to this very interesting kind of ecosystem
yeah,
where generally the notion of coaching classes are reasonably negative, so to speak.
yeah,
But
yeah,
here is
yeah,
actually a unique story, Nirmal, where you probably had some amount of positive influence. So it also means that there are few people who are probably very good at what they are doing. For whatever reason, they probably would be part of this ecosystem. Do you have any specific observations related to that?
yeah.
Uh,
Uh-huh, uh-huh. So, okay, one observation I can tell you is, I am very aware that the
mm,
bubble that we were in, the Satyamurthy
mm,
students,
mm,
especially in my days, this is
mm,
around 2003, 2004, 2005,
mm,
this bubble is definitely an exception.
mm, mm,
I am deeply aware of the. So my friend Neeta herself actually was in a different bubble in Kota, for
mm,
example,
mm. Oh,
and
okay.
the negative aspects, the negative mental aspects of those, the pressures there, the hours
Mm,
they follow, and all that. It is definitely, it is designed to stamp out curiosity, designed to stamp
mm.
out, things, doing things for their own sake and all that. So
Mm, mm,
we were definitely in an exceptional bubble.
mm.
For I mean, it's just completely good fortune for me. An accident
Okay,
of birth, I
okay,
would
okay,
say that.
okay. So it's
Yeah,
kind of an exception than a convention, right? Because
that is what I
most
feel.
of the time,
Looking around, yeah. Once I got into IIT and then I heard other people's stories, we realized, the few of us from that coaching center who got in, we realized we were in a special place. But
place.
yeah,
Okay.
yeah. But it doesn't always happen that way, for sure.
Yes,
Even in
yes.
Chennai,
Even in
other
Chennai.
coaching centers, maybe even the centers that we went to today might have morphed
Mm.
into. Seems like they are much bigger industrial complexes these days.
Yes, yes, you're
So
right.
that
So
happens.
another
Yes,
strand before we kind of
yes,
diverge is your choice of engineering physics. That
yeah.
is an
Ah, good,
important
good. Yes,
choice
yes,
you
yes,
make. That
yes.
is something I would want to know. What is the reason why you kind of chose that? And
Okay.
because IIT
Yes,
convention is that you go to IITs to do mainly kind of technology based kind of
correct, correct.
sub disciplines.
Yes, indeed,
If you can
indeed.
tell us a little bit about that.
Yeah. To be completely frank, engineering physics was the best compromise I could find between what I wanted to do, namely physics, and
Mm,
what my parents wanted me to do, which is getting a BTech from IT. Not, I mean, I'm not blaming
exactly.
my parents. I'm blaming the broader thinking. My
Yeah,
parents have been
yeah,
completely supportive.
yeah.
So that is, the social pressure of not taking a science degree from a different
Mm,
place, from a very good place, even say IISc. Back then there was
yes,
IISc.
yes.
So not doing that was entirely due to social pressure. I still
Mm,
wanted the IIT tag, the BTech
mm,
thing, and all that. But I didn't want to let go of physics. And in the prospectus that they sent us, there was engineering physics, and this was a beautiful compromise between. So that is what the frankest answer is that. If I were to do it again, I
Fantastic.
wouldn't have gone to IIT. I would have definitely chosen a BS degree
Mm.
at whatever place I got. So
Yeah, yeah, very
yeah,
interesting, very interesting. That's an important thing because engineering physics is a very fascinating subject by itself.
yeah,
Because you can see that the foundations what was laid then has probably served you very well as a researcher
definitely.
going
It
going forward
definitely did.
going forward.
Yes, yes, yes.
Because it also maybe means of course we're going to discuss a little bit this later,
Yeah,
because the choice of the problems, your research problems, are also to take up abstract aspects and try to really go into the real world and detect them. and
that
and
is
there is
right.
no bigger and better problem than detection of dark matter for a fundamental viewpoint.
That is
Is
right.
that a
That is right.
kind of a is that something you've thought about, or is it something which
Oh,
is
the
kind of
connection
by
between
accident?
engineering physics
Yeah,
and phenomenology.
yeah, yeah.
I haven't thought about it consciously, but I think you have a
Mm,
point because
mm, mm,
it because the template that I had when I got into research was
mm,
to not do anything too abstract. And
mm.
that template definitely must have come from this, the subconscious template that I had. Although some people would argue that what I do now is already abstract,
Yes.
but it's not balls and springs, or
Mm.
but nevertheless it has very real life connections.
Connections. Yeah.
Yeah, the part of particle physics that I do is, we call it
Mm.
theoretical, but that's why correct word I think is phenomenology, and it's very
Phenomenology.
much
Yeah.
bringing the theory close to experiment, and that's it.
Absolutely. Absolutely. That's actually a very fascinating thing because we're going to touch upon that as we
Yeah,
go into the next round later. So now
absolutely.
tell us about the
Oh,
transition
yeah,
to
yeah.
what
Okay,
we are
okay.
mentioning.
Right, right, right. Okay. So
Yeah.
my entry into particle physics, as I had told you in person,
Mm.
that is an
Yes.
interesting story. So the story is that for my bachelor's, okay, let's start here. Ever since Nita had happened,
Mm.
my fascination among the sciences was in physics the most. I had a little love affair with chemistry for a while in 12th standard, but came back to physics.
Mm.
Um, but even in physics, it was for optics actually. So I had
Mm.
always
Nice.
wanted to be in optics, which is ironic because
Yeah.
now I'm doing dark matter. But anyway,
Yeah.
so
Hey, but you
uh,
also actually are interested in the optical
yes,
detection
yes,
viewpoint.
yes. I like. Yeah, I want to shine light on the dark. Yeah, that's what I do.
Yes.
So, so the so so I took optics courses. A master's. We didn't have optics in engineering physics, but I elected an optics course, a master's level course, and got the highest grade possible in IT methods,
Yes.
which I'm still very proud of. And I wanted to do an optics project for my bachelor's
Mm.
thesis, but couldn't find the right advisor.
Mm.
And when things got shaken up a little bit, I ended up with a condensed matter physicist
Mm.
by name of Dr. Rajesh Narayan. He's still a very good friend of mine. I just met him last week, in fact.
Mm.
So so I was like, okay, why don't we do theoretical condensed matter for our bachelor's and see if we can pursue optics later. And in that process, I actually ended up liking condensed matter also to some extent.
Nice. Yes. Yes.
Theoretical condensed matter with
Yeah.
field theory and all that. And then I got an admission for PhD at University of Oregon, which
Mm.
had
Strong.
a strong condensed matter group as well as a strong optics group. So
Cool.
this was a very good opening for me. So what I was actually going to do, I hope I've told Rajesh this story because if he hears this, I don't know how it's going to go. But but my plan was to get into University of Oregon using Rajesh's letter and then just dump condensed matter and switch to optics.
That's a
So
good one.
yeah. So as soon as I landed in Eugene, Oregon, there was an optics conference. I registered and I went to that conference actually with the other optics guys.
Yeah.
And then I went to a couple of other workshops also in optics. I would go to the optics seminars. I took a quantum optics course, and I was doing this for a year until I realized I didn't want to do optics.
Okay. Mm.
So because something in it was not really calling out to me.
Mm.
Um, and I somehow, I felt I was not learning too much. Maybe it was the way it was presented there, or it
Mm.
just comes down to the. Oh, I'm sorry. So it just comes down to the, at that age, you always run after shiny things, and then you see that when you get in, you see it's not the shiny thing that you imagined it was, and then you get
You imagine.
disillusioned.
Yes.
So that component was definitely there. Maybe things would have been different if I were to do it today.
Mm.
So, for whatever reason, I was not very happy to pursue optics. At the same
Mm.
time, my love for condensed matter was very much on the rise because I was taking these statistical mechanics and condensed matter courses from my favorite professor till date, Professor John Toner,
Mm. Mm. Mm.
who was making the subject absolutely fascinating. And we were
Mm.
calculating things left and right, and it was incredible. Um, so, at the end of the year, I basically took a call. I felt my heart was actually in condensed matter. By some accident,
Mm.
I got into condensed matter. So, let me actually pursue condensed matter.
Okay.
Optics is not what I thought it was. I'll still read optics
Uh,
books and all that, but
uh,
but I'm going to actually marry condensed matter. That's what I was
yeah.
going to do. Except John Toner was not taking students. I persisted and persisted with him. I had hours long conversations with him about
Uh-huh.
this, but he was very apologetic, very sweet. But
Mm.
he explained to
Mm.
me very neatly that he was just not taking students.
Mm.
And very casually, almost accidentally, he suggested, if you like
Mm.
field theory and these calculations so much, why don't you try particle
Mm.
physics?
Mm.
So that's the first time anybody suggested that I try particle physics, actually. So, so, so this was around the end of my first year or second year, I don't remember, but around then, around the end of my courses in University of Oregon,
Mm. Mm.
my master's courses. After which I had to transition into research. So at that
Nice.
point,
Nice.
very, very reluctantly, I
Mm.
stepped into particle physics. I was not
Wow.
even sure that I was going to be in physics. I was thinking that I'll finish my courses, pick up my master's degree, and get out, get a job in some
Mm.
bank or some data science or something.
Mm.
That was
Mm.
my plan actually at that point. So very reluctantly, I went into particle physics, found a retired professor, Professor Deshpande, to be my
Mm.
summer mentor,
Mm.
and started reading quantum field theory books and started asking him particle physics questions. And very slowly, I realized, you know what? Actually, this is what I wanted
This.
to do in life. I didn't know this.
Wow.
I didn't know this. But this, more than anything else, spoke to me completely. This was
Uh-huh.
my calling, or this is what actually really, really spoke. This is what for me, the nascent unconscious, you know, notions of what physics is for me
Mm.
is
Mm.
this actually, where
Beautiful.
yeah, that
Mm.
so once I got in, I had the sense of inevitability. About 3 months or 4 months in, I got the sense of inevitability,
Mm.
and then I never looked back after that. I was completely into particle physics after that, and I got a great advisor,
Mm.
extremely good mentor, Professor Graham Cripps, who was, if at all, even more passionate than me
Mm.
uh, about his subject, and he was very contagious about it as well.
Mm. Mm.
Um, Contagious about his enthusiasm, and I had a whale of a time during my PhD. So that really is the foundation of my research career, I want to say. So
Oh, fascinating.
yeah,
Fascinating.
that's my entryway.
Yeah. Which also means that you've kind of taken a small detour or even a round trip across this landscape of physics,
Yeah,
and
yeah, a series of
you
fortunate
probably
events.
kind of, yeah, yeah. But it also means that uh, there's a kind of a lesson here, because a lot of students, not only just students, even postdocs and others, generally are a little bit of kind of worried if they are not making up their mind to decide on what they want to do. In fact, very few a few days ago, I was talking to an undergrad, and he was a little bit of kind of apprehensive that he's not able to make up his mind in what he's interested in within the framework of physics. And I
Right.
told him that probably is a good thing now, right? At least for a while, it's good to not to really commit to in depth into a particular
True.
problem right away.
True, true, exactly. So these days, now that I'm a faculty, I get these
Mm,
concerns too from students. And one thing I tell them is, um, you don't have to know now. And whatever you do see, whatever little that you do see within your window of physics is not the whole picture.
mm,
So
mm,
I tell some of them, why don't you jump in,
mm,
start working things out in it, and work your way through it. That's the only way you can make a better informed decision about what you really want and not. Because you do have time, actually. Uh,
yes, yes,
but at least
absolutely.
when you start jumping in, you break the symmetry and jump into it and
Mm,
explore the window that you have. At the least, you start building your stamina for research. At the least,
mm, mm,
you start learning how to learn, learning how
yes.
you do research and all that. And you have to jump somewhere into the pool to start swimming, and along the way, that is when you're going to start seeing whether you like this field and how other fields go and so on. So
Yeah, true, true. Actually, there's a quite a lot of kind of deep message there, because one will have to really jump in. Only then, as Steven Weinberg famously says, you have
yes,
to
in
jump
four
into
golden
the
lessons.
into the
Yes,
exactly in four golden lessons. And that's actually somebody I was discussing with, that is probably the most number of times I've cited that reference on my podcast.
oh really?
Maybe it's probably one of the invaluable lessons one can learn, which I'm
Absolutely.
going to anyway cite that even in this episode anyway.
Absolutely.
So yeah. So Nirmal, tell us a little bit about your PhD days. Like, now that you have figured out what is of interest to you, how
Yeah.
did you go about now building on that interest, and what did you kind of explore there?
So I had somewhat of a slow start to my research actually. So,
Mm,
well, it had to do with circumstance a bit because the advisor that I wanted was on a sabbatical first.
mhm,
So
mm,
in that year, I was an apprentice to Professor Deshpande, who was retired, but
mm,
he was still coming in. So I learned quantum field theory from him and a subject called supersymmetry.
mm,
This was all in the form of reading courses.
mm,
Um, and a big turning point was in my third year. I believe it was my third year. Yeah, when I took quantum field theory, when Cribs came back, my
mm.
advisor.
Ah,
But even then, he was not taking me as a student. He said, "I'll see how you're doing in your QFT course, then I'll decide."
okay.
But that course, nevertheless, was a very very good foundation for research because
Mm,
it was it was kind of a calculation intensive course, and QFT is the language we use for theoretical particle
yeah,
physics,
yeah, yeah,
the basic language, right? So
yeah.
that happened, and then at the end of that course that year, he gave me a project.
Nice.
And once the projects started happening, things took off really, really. And so, if you're just talking about the research stuff, I mean, after the project started, I was doing nothing but doing projects with my
Mm,
advisor, with another faculty at Oregon, and then a postdoc later, um, and with other collaborators from outside, from Fermi Lab and so on. So after that, it was all research actually, uh,
nice.
as far as physics was concerned.
So
But yeah,
the kind of foundations which you had already got exposed to, especially from an engineering physics viewpoint,
yeah,
and then you move to, of course, you probably would have also been exploring some other things. Generally, people who study engineering physics need to have also a good foundation in quantum mechanics,
yes,
because the way one studies quantum mechanics from an engineering physics viewpoint is slightly different from, let's say, if you're even starting off, let's say, as a uh, particle physics, or even for that matter quantum condensed matter or something like
yes,
that.
yes,
So you, because of the fact that you will have to have a deep appreciation of quantum field theories and
yes.
also basic foundations behind them, how did that transition happen? Was there anything kind of new and different what you had to do during that junction to really
Uh,
get deeper into that part of the problem?
Indeed, indeed. Um,
Mm,
So there again, the chronology is a little gradated here in the sense that
Mm-hmm.
the quantum mechanics course itself that I did during engineering physics, that turned out not to be very useful. Okay, in the
Mm-hmm.
sense that it was very basic. Now, in retrospect, I can see it was very basic, and
Mm-hmm.
um, and okay, frankly, the instructor was not good. So, so
Mm-hmm.
that had happened. But really, um, the the foray into quantum field theory and stuff came in the fourth year of my BTech when I took a course in classical field theory. So, although it's
Oh.
classical, okay, you don't directly use quantum and all that, but it is, how do I say this? It's a good foundation for field theory as such, and then you can just quantize
Mm.
things and think of it as quantum
Contact.
field.
Mm.
So that course was a very good foundation for how theory is done. How you
Mm.
start from equations and then you build equations that look very abstract, and then
Mm.
you have to. Somebody said physics is mostly about a vibe, right? So you have to get the
Mm.
vibe that
Mm.
this is actually physics, and then this is actually what's happening in the real world, and then you follow your nose, build up the consequences, and you see that this is really what it is. So you have to basically
Mm.
update your basic notions of what even a particle is, or a charge is, or a mass is, and so on. That is what field theory was about, the classical field theory course. So I had that, I would say that course by Dr. Suresh Govindarajan in
Mm.
IIT Madras, that
Nice.
really trained me for theoretical physics. And
Mm.
then going into
Nice.
Oregon, when we had graduate level courses, there we
Mm.
redid quantum mechanics, graduate level quantum mechanics. Now that was again a really strong foundation that I really needed.
Strong. Strong.
Yes, yes,
Mm.
to go to
Mm.
quantum field. So
Very,
in
very interesting.
engineering physics itself, in IIT Madras at least at that time, it was
Mm.
somewhat of a, because it was a new program. Uh, the syllabus was still being determined. So what happened was the physics professors taught it like physics, and then we had to
Mm.
take electrical engineering courses as mandatory requirement, and those were electrical engineering. So it was like actually a,
Mm.
an immiscible mixture of
Mix.
physics and engineering. Actually, they had not yet dovetailed these things very well together. I think
uh,
it's been updated today. I think so.
Today. Okay. Nice.
Yeah, yeah,
Nice. Yeah, these are very strong programs because I've heard and I also know a lot of people from IIT Bombay who did
yeah,
engineering physics are all now doing very interesting
yeah,
research in physics.
yeah,
Even
yeah,
in
yeah.
JNC, I know at least three people, at least two, three people, including Umesh Wagmare, Shobana Narasimhan,
Uh huh.
and even probably even KS Narayan and other people. So yeah,
Uh
so
huh.
this is very kind of fascinating to kind of to know that
Yes.
you found this kind of uh, resonance with the professor whom you also started kind of interacting with, and
Yeah.
you also are now learning on your own, probably even exploring things on your own. And one of the very interesting aspect is that once you are becoming kind of quasi independent during the PhD days,
Yeah.
you are probably not only just looking at the problems and also working on problems which are assigned by your advisor, but
Yes.
probably you would be also asking yourself some questions,
Absolutely.
which generally happens to have very good kind of extrapolations to your future career. Were you
Absolutely.
thinking
Yes.
about questions? Yeah, could you please tell
Very
us
much.
about it?
Oh, yes, very
Yeah,
much, very much. So,
yeah.
and I would inundate my advisor with such questions,
Mm,
and he would, he wanted me to finish projects for very good
mm,
reason. So
mm,
this happens to
mm,
students
mm,
all the time. I mean, now I
mm,
realize it
mm.
very much. As students, when we get very excited, we have wall-to-wall ideas. We don't know which ones work, which ones
Yeah.
stick, and all that. So he wanted me to finish projects, and he would be like, "Oh, then yes, this is a very good question for a journal club." Or he would say, "This is a very good question for you to pursue after you graduate." But I did. That's what actually I
Yes.
noted down all my questions, and some of these did turn into real projects during my postdocs, and I'm actually very,
Wonderful.
yeah, very heartened by that. So yes,
That's
so he gave me the freedom to basically. I mean, he didn't. He There were no hours or anything like that. His was results only work and mind. You go
right.
wherever, you
Mm,
come whenever, you
mm.
collaborate with whoever. As long as we are producing good things and we are
Yeah.
discussing physics, we are good. And that really was what. I wanted, and worked out really well. And yeah, and laid the
Fantastic.
seeds for my future stuff as well.
So, yeah,
So can I say
because that
one
is a
little thing
very,
here?
yeah, yeah,
One
please,
one quick
please.
thing I want to say here is, so during my PhD, I my PhD actually is in collider physics and
Mm.
theoretical physics in supersymmetry. But I had always wanted to branch out and go do what I still call space physics, in the sense that particle physics in space, astroparticle physics.
Mm. Astroparticle.
Yeah, yeah. Um, well, what anyway? I had question. I had a lot of questions in astroparticle as well back then, and all that happened after my PhD. All that happened.
So, give us a gist about the problem you worked on for your PhD, like a basic
Indeed,
element as yeah,
absolutely, absolutely. So okay,
yeah.
um, so the while I was doing my PhD, the LHC had come to fruition, and the Higgs boson was discovered during the course of my PhD. In fact, my
Oh,
first paper,
okay.
um, not by coincidence, came out on archive the day the Higgs boson was discovered. This was because 6 months before we had all heard the rumor that the announcement was going to be on July 4th, 2012.
Mm.
Professor Spencer Chang and the three of us students basically started working on a project
Mm.
related to the Higgs boson, and we finished it by June and put it out on July 4th. Um,
Nice.
so, so that happened, and naturally, like many graduate students in particle physics at that time, my PhD was based on the LHC. In fact, my PhD's
Mm.
title is Supersymmetry and Dark Matter in the
Yeah.
LHC era. So
Era.
I knew
Yes.
I put the
Yes.
word era in because I knew that in the
Ah,
future people may not work on the LHC. The LHC may not be so popular. So I wanted to put the word era even back then, so that it would look like a historic thing in the future.
it is. It is indeed.
It
In
is,
fact, that's
yeah.
yeah. Yeah.
So
Wonderful. Wonderful.
yeah, yeah. So that was one paper, and with my advisor, what we did was um, a couple of projects I did with my advisor. One was on looking for um, the effects of dark matter in
Mm.
the quantum amplitudes of well-known processes at the LHC. For instance, a very clean process at the LHC is basically a quark and an anti-quark. You get a quark from one proton and anti-quark from the other proton because two protons are
Mm.
colliding, right?
Mm.
You get
Mm.
a quark and anti-quark in the initial state turns into an electron and an anti-electron in the final state.
Mm.
So this is called the
Mm.
Drellian process. And in the Standard Model, you exchange a photon or a Z boson to get this. So, so these are quantum amplitudes, and you have the Feynman diagrams and all that corresponding to the amplitudes, right? So our idea was you can have a third amplitude with dark matter and its friends meaning other dark sector particles,
Mm.
going around in some loop in the Feynman diagram. That is basically they take part in the total amplitude. In which case you get interference effects with the Standard Model. So this
Mm.
interface with the Standard Model, and it happens in a very non-trivial way because now you have these loops in the diagrams, and there are things like threshold effects and so on, and you get very spectacular spectra, energy spectra
Mhm.
of the final states. So energy spectra I did in my PhD, but I wanted
Mm.
to pursue angular spectra because Rutherford, for example, discovered
Yeah.
the nucleus through angular spectra, right? So I pitched this to my advisor. He said, "Go do it after your PhD," and I did. I wrote as soon as I finished my PhD, I wrote a single author paper in my first postdoc,
Yes.
angular spectra.
In fact, I actually see when I was just looking and doing a bit of research, there is also a very interesting topic on which you have series of talks, specifically on the Rutherford part of it.
Yeah,
In fact,
yeah.
it is very intriguing because the title of that particular talk is
Reverse.
related to Rutherford reverse Rutherford scattering.
Yes, 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 yes.
What do you mean by reverse Rutherford scattering?
Okay, I'll tell you.
Vis-a-vis
Okay.
conventional
Yeah,
scattering?
definitely. Yeah, yeah.
Yeah.
So this is related to stuff that I've been working on after my PhD. So this is
Mm.
actually astroparticle physics.
Mm.
But the idea, so the reason I came up with that title is, um, so There is a class of experiments that look for dark
mm,
matter, um, where you put a detector underground
mm,
and
mm,
you imagine that there is a flux of dark matter passing through your detector. Okay, I say imagine because nobody can tell this for sure. Nobody can really tell what the flux of dark matter is, because its
mm,
mass is unknown and all that. If dark matter is a particle, its mass is unknown, so its flux is unknown. Its number density is unknown, so its flux is unknown. So so you have a monolithic detector sitting inert, and
mm,
a near isotropic flux of dark matter falling in, and probably scattering with the particles sitting in the detector. If if that scattering happens, then you will detect it as
mm,
some nucleus shaking out of nowhere.
mm,
Something invisible
mm,
came and just pushed the nucleus, right? So this goes by the name of direct detection. That is, you're trying to detect dark matter directly with a detector.
mm,
I
mm,
like to
mm.
call it reverse Rutherford scattering because what Rutherford did was his beam was made up of well-known particles,
Yeah.
alpha particles, and uh, he hit the target not really knowing what he was hitting. The target was unknown.
Mm.
He had to discover the nucleus this way. Whereas this is reversed. Here you know the target, you don't know what the beam is made of.
Got
You're
it.
waiting for a beam.
Very nice.
So
Very interesting. Very interesting. This is fascinating because then you're essentially kind of inverting the problem of the fact that the flux is what you're interested in,
exactly,
and
exactly.
you are questioning what is the flux content
Yes. What is the
while
flux
looking
content?
at.
Exactly. By studying changes in the target, by studying the energy
Mm,
momentum of the
yeah.
recoiling target, you can
Mm,
say something about the interactions between the target and a possible dark matter particle, such as
particle cross
the
sections.
cross section and the mass of the dark matter particle.
Mm,
So that is what we are trying to do. So this class of experiments has been going on for 4 decades now.
hmm hmm
Since
It's
yeah,
an underground experiment.
they're usually placed underground because
Mm,
they want to shield against cosmic rays,
mm.
which can give you a huge background. But for special cases, they also put it on the surface of the earth.
And very
Yeah,
very interesting. Very interesting. So we'll continue in terms of your trajectory. Now that you're
yeah,
finishing your PhD, you now probably move to Notre Dame,
yeah. I
if I'm
went
correct.
to
Right?
yes, University of Notre Dame.
Yeah.
So we say that Notre Dame is a university in America, and Notre Dame is a church in
Church.
France.
Yes. Okay. Yes.
So
Yes. You're right.
we just yeah, deliberately say Notre Dame. So,
But I hope the church actually had a problem. You know that, right? The fire
oh
and
yeah,
they
of late,
collapsed.
That's why, yeah. Even more reason to call it Notre Dame. Safeguard ourselves from.
Yeah. So tell us
So
about that transition, because also uh, you're uh, you're probably going into a stream of research which becomes far more independent in nature,
yeah,
and
yeah,
that's a transition which is important for us to understand.
indeed.
Yeah. Mm,
So um, I would say that while it was happening, I enjoyed myself a lot. That transition of it's getting a lot more independence, and the fact
mm,
that you can choose your like the angular distributions I was talking about, right? So I just wrote it
mm,
on my own.
mm,
So that was
mm.
very exhilarating. That kind of independence. I couldn't believe that they're giving me a salary and a parking lot spot,
Mhm.
for for doing physics, for just going to the office, and I'm doing physics here. Actually, why are you paying me?
Yeah.
So that was very exhilarating. But
Mm,
looking back, I feel I struggled a lot. I enjoyed my struggle back then, but I struggled a lot in the sense that in the back of my head, I think I was in denial back then, but in the back of my head, definitely I was worrying a lot about where this is all going.
mm,
So I had just got married as well. So just after my PhD,
mm.
and so just after actually my wife was still working in Portland, and I had gone to India now. So we were 1,800 miles apart. So that was
Yes, yes,
also
yes, yes.
really eating into our mental health.
Mm,
And so at what cost is this independence? That was definitely nagging at me, at my wife a lot more than me, but it was nagging at me.
mm,
It was
mm,
eating,
mm,
just really cutting into my psyche also. Um, but research wise, I couldn't have asked for a better transition. So I was learning to be independent, trying to shed my studentness, but couldn't do it completely. I don't think I can
mm.
never stop shedding my studentness.
Never, never. One should never
No.
do that.
Yeah, okay, I'll never do that. Thanks. Good to hear that. And mentoring students, grad students. I mean, the students saw me as one of them, and that was very heartening.
Nice.
So mentoring them was actually a lot of fun. We wrote papers separately from the faculty and all that. We brainstormed
Mm,
ideas from scratch and wrote them up. All that was amazing. Um, but field wise, that is when I met my very good friend Joseph Bramante, who was a fellow postdoc there. We overlapped for a year. The year I
mm,
joined was the year he was his last year. And I would just, shamelessly tell him, "Oh, I'm so jealous of what you do. You're doing all this," because he was an astro. He was trained a little bit in collider physics, but also in astroparticle physics, and he's a very good astroparticle physicist himself,
mm,
cosmologist, astrophysicist. I mean, he's just everything
mm,
actually.
mm.
And I would just tell him, "Oh, I'm jealous of what you're doing." I don't know if it was because of that or something else, but he basically just roped me in to
Mm,
uh, a project that he was doing in a part of a series of things that he was doing based on neutron stars,
mm,
compact
mm,
stars, and dark matter. So that paper, that project, which became a paper in April 2017, and this was about 2 years after my PhD, that
mm,
is my starting point in astroparticle physics. So by then, my transition from collider physics was almost complete. I still wrote one or two collider papers after that, but by now I had started clicking into astroparticle physics,
mm,
and in a sense, this is really what I had been wanting to do since close to the end of my PhD, and this felt like it gave me wings.
mm,
Now I had so much more to learn, and so many. It felt like the number of people that I could talk to had doubled. It felt like so, and it completely caught my fancy. Uh, so I just jumped into it again. Or I made the switch once again, a sub switch,
nice.
you can call it. And I probably got my next job at Triumph, and definitely this
Mm,
job, my faculty
mm.
job today, on the strength of my astroparticle career.
Career. Yeah.
Yeah, yeah, yeah,
That's very nice. So before we make that transition,
yeah.
we have to first talk a little bit about your subsequent kind of progression into another foray into northern part of America, but slightly more north into
Yes,
Canada. Probably
yes,
you
yes, yes.
move into Canada. Could you please tell us that transition and what is the kind of work you ventured into there?
Right, indeed, indeed, indeed. Okay, so at Notre Dame, I had already written maybe two or three papers in astroparticle physics. Um, and when I went to Canada, Triumph, which is a national lab in Vancouver,
Mm, mm,
um, almost everything I did was astroparticle physics. Um,
mm,
it was more of dark matter. Almost everything was about dark matter. So I wrote 20 papers when
mm.
I was at Triumph over
Wow.
4 years,
Okay.
and yeah, I mean,
Mm,
yeah. Also, Triumph was my most productive year. So I was basically just becoming more and more experienced. I was just
mm,
thinking
mm,
faster and
mm,
meeting more people, more ideas, more collaboration. It's just down to experience. Just getting it,
mm,
a lot of experience very fast.
mm. Yeah. Yeah.
And of course, very key to this was the work environment. Very, very supportive
Mm.
work environment. Uh, and home environment. Very, very supportive wife.
Exactly. So
Yes.
you so
So,
but you
that.
got together. You could get together. That is a
Oh, yes,
crucial
yes, I
question.
forgot to say that. Yeah, 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 yeah,
Yeah.
yeah. That, I cannot place any value on that. We
Nice.
finally, we completed our marriage in the sense that we finally actually,
Yeah.
we finally got together in 2018 and started living under the same roof for the first time ever, actually. Although we had
Wonderful.
known each other
Beautiful.
for like about 2 decades. So, So okay, so that definitely was a big boost,
Mm, mm,
and the work environment was also absolutely fantastic.
mm,
Very free, and very productive. So the most frequent collaborator I had there was David McKean, and
mhm,
he somehow, I think this is the reason he hired me. He had exactly the complementary uh, know-how that I had. So we both had
mm,
the same philosophy, the same, a lot of things between us clicked. We had a great chemistry, but he had
mm.
exactly complementary know-how, and
Complementary know. Yes.
this led to a very productive collaboration. Actually, me
Mm,
and Dave Megan,
mm,
we wrote a lot of. I think he's my most frequent collaborator today.
mm.
We wrote a lot of papers on so many different topics, very diverse topics, and somehow we just completely, inspired each other, I guess.
Wonderful.
Yeah, yeah. So there, I actually, yeah.
Is he still at Triumph?
He's still
He's
at Triumph. Yeah,
he's
yeah.
still
He
still at Triumph.
when I joined as a postdoc, he joined as a faculty. I had known him before
Nice.
also.
Nice.
I had known him when he was a
Ah.
postdoc.
Mm,
Um, so so that had happened. So while at Triumph, actually, I also started doing some pure astrophysics projects. Now I had, from colliders in PhD, I had gone
mm,
completely into astrophysics. Some of them were pure cosmology.
mm,
Um, and I also did one collider paper with my advisor. My advisor actually, when I met him once, he was like, he had an idea, but he somehow still thought of me as a
mm,
collider person. But it was a very awesome idea. So myself and Dave
mm,
Makin and Cripps got together and wrote a very good collider paper as well.
mm,
And a couple of papers I wrote were not on dark matter. These two papers I'm very proud of because they are based completely on the standard model, which
mm,
means there's nothing speculative about it.
mm.
uh, so it's something based on nature as we know it.
Right.
So this is
Nice.
on supernova neutrinos. Um,
Mm, mm,
so I had this was those 20 projects that I did was, my playground very much expanded,
mm,
and I felt I became even more of a complete physicist. This was always my goal. I wanted to be a diverse and complete physicist as opposed to go very deep into some niche and
go
not
deep.
really know about the outside.
Okay.
So,
Yeah.
so
Yeah.
those dreams came true at Triumph, and I did become,
Wonderful.
yeah, yeah. Anyway,
Yeah. No, it's wonderful. So is that the time where you were also involved in this particular experiment, which is acronymed as
yes,
Deep
yes,
3600?
that's right,
Could you
that's right.
tell us a kind of a gist of that, a little bit about what is that experiment about?
Totally,
Because there
totally.
is some argon pulse shape is there. I don't know what
That's
does
right.
that mean. If you could
Okay,
elaborate.
okay,
Yeah,
sure,
yeah,
sure, sure.
yeah, yeah.
Yeah. So, okay, sure, sure. So, um, first, let me tell you the idea of,
Mm,
how the idea, what the idea is, and what this experiment did for this idea.
mm,
So
mm,
the idea was that I told you about the underground detectors. They've been looking for dark matter for about 4 decades by just looking
mm,
for the beam, right, and scattering of the beam. Now, the particular signal that most of these experiments are looking for is there's a flux passing through, but during the transit of each particle in that flux, you expect at most one scatter as the
mm,
particle passes through. At most one. And really, what they're waiting for is they wait for a year or so, a time scale of a year,
mm,
and in that year, if they get one scatter, they're happy.
mm, mm.
So because you expect dark matter to be very weakly interacting,
Weakly. Mm, mm.
so it's a very feeble interaction, is what you expect.
Feeble interaction. Yeah, the cross section itself is very
It's
low.
very
So
small, exactly,
it's
exactly. Cross section itself is very small,
mm,
but
mm,
it need not be so actually. So this weakly interacting paradigm basically comes from I would just call it a theoretical bias that
mm,
we haven't seen dark matter, so it has to be very weakly interacting. But also, if you it turns out that when you combine particle physics and cosmology, you find that uh, in the early universe, if you had weakly interacting, but now I'm using the word weak with a capital W. I'm thinking
mm,
of the weak force, the one of the four fundamental forces.
mm,
If you have a dark matter particle with um, that weak force interaction at a weak force mass, electroweak
Mm-hmm.
interaction cross section at electroweak
Mm.
mass, then you find that miraculously the amount of dark matter that you can make in the early universe from just thermal considerations, just putting dark matter and the Standard Model in a thermal path, the amount of dark matter that you would get from this matches with
Mm.
the observation, with
Ah,
cosmological observation.
nice,
So this is sometimes called the
nice.
WIMP miracle. The WIMP stands for weakly interacting massive particle. It's not a
Mm.
miracle; it's a
Mm.
coincidence. But
Mm.
people like to be
It
blind.
works. It at
Yeah,
least
it works.
in
It
terms of
works very well. So it's a great coincidence. So because of this bias and the generic psychological bias that dark matter should be just weakly interacting, because otherwise, we will
mm.
see it.
Mm.
Um, the experimentalists, by and large, look for this very feeble scattering interaction. But there's nothing really that stops dark matter
Mm.
from having actually very strong interactions. And
Mm.
the reason is, if it is very strong, um, then if the detector is underground, the dark matter could, by the time it goes underground, it scatters the same interaction that you're looking for, the nucleus dark matter scattering. The same scattering could happen multiple times in the Earth's crust before the dark matter
Mm.
gets underground, if the cross section is large. In that case, the Earth's crust basically slows down the dark matter,
Mm.
and you
Mm.
just don't see it underground.
Yeah.
So this is one reason why we don't see any events underground in the underground detectors, because we get all the dark matter. It's just that they're all slowed down, or they just
Slow
stopped by the
down.
Earth.
Yeah.
So that
Yeah.
could
Yeah.
happen. There is room for that to happen. There's a lot of room for that to happen. The other reason is maybe the dark matter particles are so heavy while remaining particles, but they could still be elementary particles, but they could be so heavy that the number density is very small.
Mm. Mm.
Because we only know the mass density of dark matter by studying stellar motion and all that. From
Yeah.
astronomy,
Yeah.
we know
Yeah.
the mass density, but the number density we don't know. If the dark matter is heavy, the number density is so small that you might wait for a few years, but not a single dark matter particle would have gone through your detector, leave alone scatter.
Gone through the. Absolutely.
So you're
Absolutely.
limited by the flux. So, um, so the idea was then to why okay. So now the idea is maybe a lot of this multi-scattering dark matter with high cross sections is getting at the detector. It is
Mm.
scattering a lot in the detector. It's just that because these experimentalists are particularly looking for the single scatter, they are throwing out all the data with the high energy units, that is the high scattering units
Nice.
for analysis.
Mm.
So this might have been going on, is what we had written down. So don't throw away that data. Please analyze that data also, and in the future, keep all the data and analyze the high scattering data also, because you can still cover a lot of parameter space in cross sections and masses, especially these high masses and high
Mm.
cross sections. So this was the idea. We had written this up in a couple of papers with in collaboration with experimentalists. Joseph Bramante was part of
Mm.
this as
Mm. Mm.
well. Then I happened to pitch this to a person in Triumph who was an experimentalist in Deep.
Mm.
And
Mm.
he asked me to give a talk to the Deep collaboration about this.
Mm.
And they were sold by this because Deep had, at that time, they had the biggest dark matter experiment on Earth
Mm.
by size.
Mm.
And big is good
I
for
see.
this kind of search because if
Mm.
it's big,
Mm.
then you admit more flux, and hence you can go to the highest masses.
Got it. Very
So
interesting.
immediately there were four very interested collaborators at Deep, um, and a working group was formed. And I was very, I mean, it was a very pleasant surprise to me that they asked me to be on the working group and that I would be on the paper as well. So it's not like I wanted to
Nice.
be on the experimental paper. They invited me, and I
Mm.
was more than happy to be on that. So that is how it happened. Now, it turns out that what I said, it's a cartoon picture. You have dark matter scattering multiple times in transit,
Mm.
um, but for every detector, you need to understand its detector technology to pick out this multiple scattering.
Multiple scattering. Yeah.
Yeah. So at deep, they use liquid argon as the detector material, and they what they see is basically the scintillation of liquid argon. when a particle hits a liquid argon molecule, it scintillates within a certain time scale, basically. Um, and so that is where the pulse shape comes in.
Mm, mm,
So I'm a bit rusty on the details, but it basically comes down to there are a couple of dimers of liquid argon. If you have energetic recoils, then there is a characteristic timescale for that pulse. If you have a low
mm.
energy recoil, there's another characteristic timescale for that pulse. So
Nice.
they need to look at the pulse shape, and using the
Pulse shape.
pulse shape, they discriminate between energetic signals that would come from hitting a nucleus, such as dark matter hitting a nucleus, or
Mm-hmm.
a low energy pulse like an electron recoil, which would come from uh, radioactive isotopes sitting in the detector decaying,
Isotopes.
basically.
Mm.
So
Nice.
that's the
Very
idea. That is,
fascinating.
yeah, this is what they do. And now the
Fascinating.
game was to now devise a search where you don't see one pulse, you see a train of pulses.
Mm,
Now, this is a
mm,
hard problem. This is definitely a hard problem because the pulses might merge if there are too many scatters.
mm,
Or there
mm.
may be few pulses and you may not distinguish them as separate pulses and so on. So then
Yes.
other
Yes.
things came into the picture. So we did the search for 2 years. It took
Wow.
us two
Nice.
years to set
Nice.
up and get the result. So
So
that's the,
this was the part. This was the part of the study in PRL where scattering
yes,
searches in
yes,
for dark matter, right? That is the one.
exactly, exactly.
Interestingly, that also has that old rocks as part of the title. That
Oh
means
yeah,
that it means that it's part of the Earth kind of substance, right?
yeah, yeah.
Like
Sorry, sorry,
when
sorry.
you call.
This is different. So you're talking about scattering searches in neutron stars, cosmic rays, and old rocks.
Yeah. Yeah. You're right. Yeah.
Okay,
Yeah.
okay.
Yeah.
No, that I would say is quite divorced from this. This is
Mm,
in
mm,
a
mm.
controlled environment. You're looking for dark matter
Okay.
scatterings in a
Okay. Got
different
it.
way.
Got it.
So there, so that was us piggybacking on other people's ideas, the old rocks
Uh-huh.
part.
Mm, mm, mm.
Looking for dark matter in old rocks. That's also a very interesting idea. That's also been going on
Yeah.
for I think 3 decades now. I think they started this in the late 80s or 90s, and now it's come back in earnest. Some groups are doing
Mm,
this very
mm.
much in earnest. Here, the idea is that okay, either you build a very big detector and wait for a few years within human lifetimes or graduate student graduating times,
Yeah.
PhD student graduating times, and you get the data within that. That is your total exposure. Either you can do
Mm.
that, or you take a very small detector and you wait a billion years.
Yes, yes.
So now you might even get much bigger exposure than the other method.
Yeah,
So
yeah.
and where do you get a billion-year-old detector? These paleo rocks, which were formed billions of years
Yes.
ago. You go
Yeah,
deep in the
yeah.
earth; they are already shielded from cosmic rays. You pull
Mm,
them out,
mm.
and then you see. And dark matter has also been around since the beginning of
Wait,
the universe as we know it.
universe.
So as soon as the Earth got formed, dark matter, if it has scattering interactions, especially the kind that I talked about, if it has strong scattering interactions, it goes in, hits the mica or whatever, because mica seems to be a very good
Mm,
rock for this, and it might have left characteristic tracks. So you look for these tracks with chemical etching and other techniques, and if there are no tracks, that's also good because you can now eliminate what dark matter is not.
mm, mm. Yeah.
But if you see tracks, then you can investigate further. So that's the idea there. Anything is a
Fascinating.
dark
So
matter
we
detector,
tack
actually.
exactly anything which is part of Earth can potentially become that. Yeah, that's true.
Absolutely,
Very
yes.
nice. So now we'll make the transition to your current position, where you have now
Oh,
become a assistant
yes,
professor at Indian Institute of Science in Bengaluru. So you started in March 2023,
yes.
and tell us about the transition from a postdoc who has been extremely productive and also doing cutting edge work, and now making a transition to India. Tell us a little bit about that transition.
Okay, okay, absolutely. Oh, so it's been nothing but a thrill ride or a joy ride ever since I got here. For one thing, so this angst of where is the future going and
Mm, yeah.
where are my wife and I going to settle? This
Mm,
was really eating into us a lot, especially in my second postdoc. Once you hit your second postdoc,
mm. Yes. Yes.
that becomes that just intensifies, and
Mm,
the job market. in theoretical particle physics has of late has not been that good. It's a slightly fluctuating market, but overall it's not been that good.
Yeah.
So it was really not clear to me if I was going to be in physics. So that was
Mm,
really, really bothersome. I mean, more than bothersome, very dark actually.
mm, mm, mm.
Um, so living on the one hand, all these great things were happening. It was like the best of times and the worst of times. On the one
Mm,
hand,
mm,
things were good. On the other,
mm,
thinking of the future was not good at
mm,
all. So to have come out of that and got this position in and of itself actually was, I mean, it was seriously stuff of dreams.
mm.
For that mentality. So that was great. But we had also started making plans to come back to India anyway, even if I was not going to be in physics
Anyway.
and all that. We were going to come back to India anyway, for
Oh,
various
okay. You're
reasons,
not
family
for
reasons,
reason.
and
Okay.
yeah, yeah, exactly. Um, so I couldn't have gotten a better position than here, actually.
Mm,
For my family is not far away, and
mm,
we love Bengaluru. I love IAC. So
mm,
IAC was one of the best places I've interviewed at in India. So absolutely, and the transition was everything that I dreamed of. I mean,
yes.
I had you can't help visualizing what will I do if I become a professor, how will I talk to students, and how will my colleagues be, and all that. So
Mm,
absolutely, all of it has come true this year. I hope
wonderful.
I hope
It,
things continue to be positive in the coming years.
it will. Yes.
Um,
Yes.
and another very big reason why I'm enjoying this is I have very, very supportive colleagues at the Center for High
Mm,
Energy
yeah.
Physics.
Yeah. Yeah.
Um,
Yeah.
very supportive, very open, very approachable. So that helps a lot. Very trusting.
Absolutely.
So
Absolutely.
so yeah,
Yeah.
yeah.
Wonderful. Wonderful. So, what is your current research interest in terms of your own group? And tell us a
Indeed.
little bit about that. Yeah.
Okay. So currently, I have in some official capacity 3 PhD students.
Mm,
Um, and I'm also working on a project with a couple of undergrads, and I'm working
mm,
with a
mm,
master's person. So all of these projects, in some way or the other, have to do with dark matter, but we are exploring different aspects of it.
mm,
Um,
mm.
so maybe I'll touch upon a couple of these.
Yeah. 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 Yeah.
Okay,
Please.
so one of them is so there's a student called Avinash here. So he's an expert on pulsar timing arrays. So
Mm.
these are so the pulsar timing array is actually done in Pune, by the way. It's GMRT that's doing
Mm.
it.
GMRT. GMRT.
Yeah,
Yeah. Yeah.
yeah.
Yeah.
So the Indian pulsar timing array. He's part of that collaboration,
Mm, mm,
and
mm,
they look. So they basically time pulsars, which are neutron stars that as they rotate, they pulsate, and neutron stars rotate with such great regularity that you can use them as basically your metronomes. Metronomes almost at the
mm.
precision of
Metro.
atomic clocks,
Wow.
right?
Wonderful.
Yeah.
Mm,
Uh, so because you have such good timing data in the sky, you can start looking for all sorts of interesting things. And this
mm,
year, there was a big news splash from various pulsar timing arrays around the world, including Indian pulsar timing array, on the detection of gravitational waves
mm,
from the early universe, basically. Not from the early universe, actually. Gravitational waves emanated by all the supermassive black holes in the universe merging with each other. So that gives you a stochastic
mm,
background from an isotropic stochastic background. So and they've detected that basically
mm,
uh, because the gravitational waves will stretch and squeeze space in our line of sight to
mm.
these pulsars, and that would mess with the timings of the pulsar arrival times, right? So
Nice.
that's a signal.
Nice.
Now you could also look for dark matter with this, some special kinds of dark matter. And one
Mm,
of these pulsar timing array collaborations called Nanograv, based in North America, has already published some results on uh, looking for dark matter with this. You could, for instance,
mm,
have dark matter that is so light that it basically acts like a field sloshing around
mm, mm.
right here in this room and your room, basically. It's just invisible, so
Nice.
we can't detect it. So it's so in that case, this wave-like or field-like dark matter, um, if it has very feeble couplings with the electron or the neutron or proton, because it
Uh-huh.
is sloshing around, it will make the masses of these particles oscillate in time.
Mm,
So
mm.
literally, the masses of electrons and photons, etc., are oscillating in time through their interaction with this dark matter. If
Nice.
that is the case, because now you have such a precise metronome,
Mm,
you're not messing with the masses of neutron stars, right? The neutron star mass
mm,
also is oscillating, so its angular momentum is oscillating,
mm,
and that will
mm,
be picked up in these timings. So we're trying to import these ideas and mix our other ideas for the Indian pulsar timing
mm.
to get to
Nice.
because the Indian
Very
pulsar
interesting.
timing has its own technology and its own frequency band and all that. So you get unique
Mm-hmm.
parameter space at in PT. So that's one. So this is so I had no expertise in pulsar timing arrays until I met Avinash. So he's the one who's
Wonderful.
driving. Yeah, yeah, yeah. So this is one of
Fantastic.
the perks of being faculty, I guess.
Yes.
You never stop learning from juniors.
Yes. Yes. Absolutely.
Yeah.
Absolutely. Absolutely. Wonderful.
So yeah,
Wonderful.
yeah. So with another student, what we are looking at
Mm,
is
mm,
another thing that India is actually a pioneer in now. Um, that is the Daksha satellite, which will get
mm,
launched by a few institutions, and one of the leads of this is Varun Bhalara at IIT Bombay.
IT
So
Bombay.
I had met
Yes.
him when I interviewed there actually, and he told me about it.
Mm, mm,
But the Daksha satellite is going to be an X-ray satellite. It's actually a couple of satellites that will be
mm,
orbiting Earth, and it will monitor gamma ray bursts basically. And gamma
mm,
ray bursts,
mm.
their sources are thought to be merging neutron stars or core collapse supernovae in the far universe, being just very luminous in gamma rays basically.
Nice.
So, so that is the main mission of Daksha. But as I said, everything is a dark matter detector, right? So Daksha themselves realized this, and they realized that they could look for dark matter in
Mm.
the form of primordial black holes. So now we are not talking about ultra light dark matter; we're talking about ultra heavy dark matter. Actually. Dark matter,
Heavy dark matter.
yeah, dark matter, the masses of asteroids and so on,
Mm,
but in the form of black holes, and that's completely possible. Black holes are electrically neutral; they have mass and all that, so they totally fit the bill for being dark matter. Um,
nice. Nice.
so, and they could employ a technique called microlensing, where you look for the bending of starlight traditionally. Um, and due to the bending in GR, you also get a magnification of the intensity
Mm-hmm.
of that star. And
Mm.
looking for these magnification light curves, basically. That's the technique of microlensing, and they realized that Daksha can do some very nifty things because they have two satellites. Because they have two satellites, they can
Mm.
now start doing parallax measurements.
Mm. Mm.
So just like our two eyes, so they can,
Yes. Yes.
yeah. So
Binocular kind of.
exactly, exactly.
Mm,
And so they have more handles on microlensing, and because they're monitoring GRBs anyway, the GRBs are gamma ray
mm,
bursts, which are cosmological distances away. um, they can look for primordial black holes that intervene the line of sight between us and these gamma ray bursts all
gamma
along
rays.
between us.
Oh.
So they've already written a couple of papers on this. Now Manish and I are extending this to
Mm,
other dark matter candidates, not just primordial black holes. And we're also trying to
nice.
see if some improvement in detector configurations can help us get even more parameter space in these kinds of dark matter.
Wonderful.
So that's the
Fascinating. Fascinating, Nirmal. Nirmal, I want to also kind of now slightly broaden the scope of the discussion, and
totally.
in the next few minutes we going to get a gist about your interest in science communication.
Yes.
That is something which is very interesting because now gone are the days where scientists can sit in their ivory towers and pontificate only about their research. And I see that you have been actively involved, not just in recent times but over a long period of time, where you have been involved in communicating science, not only just only as a small kind of an adventure, but also with reasonable seriousness. So, first of all, what motivates you to do that? And second is, what is the kind of things you are interested in within the framework of science communication? And thirdly, I would want to ask about a very fascinating paper you have written, where the title of the paper is Names from Greek Myth in Fundamental
Oh, yes.
Physics. I had a look at it. It's fascinating. I'll be anyway linking in the show notes. But
Yes.
from the science outreach viewpoint, your motivation, and also this particular aspect, please
Ah,
tell us a little
oh,
bit.
absolutely. Okay.
Yeah.
So my motivation is this is going to be hard to articulate. It's it's very very intrinsic. That's why it's hard to articulate. So my motivation is
Mm,
probably that I cannot separate science from the communication of it.
absolutely,
You know, I
absolutely.
cannot do it actually. I mean, ever since I started getting interested in science, I couldn't help talking about it or I couldn't help listening to people who talk about it. And
Mm,
to me,
mm,
that is the way science is. You learn, okay, you go into withdrawal, you do your calculations.
mm,
I get a lot of delight and pleasure and wisdom out of that as well.
mm,
But what
mm.
is it that you are doing at the end of the day? If
Mm.
I don't explain it, it's not complete for me. I mean, at
Yeah,
just a personal level, I'm not talking about how it reaches the others and so on. If I don't finish
absolutely.
that explanation of it to people, to experts on the one hand, to non-experts on the other hand, to my friends, to my wife, to my brother, to my parents, if I don't do it, it's not complete to me. That aspect of doing
Mm.
science is not complete to me. It just comes down to that. So that is why it's hard for me to articulate. It's very intrinsic.
Absolutely,
So,
absolutely.
uh, but that is my fundamental motivation. During my postdoc, another motivation actually started coming to me. I think I touched on this when we met.
Mm,
The
mm, mm,
motivation, which that motivation is guilt. Guilt
mm,
because I am getting so much pleasure out of doing particle physics, being in this field, meeting all these amazing people, having my very unique experiences, unique stories. But what
mm,
am I really doing to people? I'm a people person, I think, and
mm.
what am I? I'm not really. I'm getting all this, but really, I'm not reaching out. I'm not really touching anybody's lives.
Yes,
And when I
absolutely.
started getting into research, my maternal grandmother, the words of my maternal grandmother actually started raining down on me. She said, "Whatever you do,
Mm.
make sure that it goes and reaches people. Don't."
People.
There has to be some use for it. And particle physics is one of the
Yes.
most useless things, actually. uh, I mean, it has produced a lot of useful things in medical
Mm.
science and so on. But
Yeah, yeah.
the questions that we pursue are not for the use of it. The
Use,
use,
use.
the use
Absolutely.
comes
You're
out
right.
of it.
You're right.
Um, so that guilt really started eating into me, especially in my second
Mm,
postdoc. And so I didn't know how to channel it and all that. And I had
mm,
expressed this to one of my good friends, Flip Tanido, who's a faculty at UC Riverside,
mm,
and he suggested, why don't you write to middle school kids? He told me there's a program. It's called Letters to
mm,
Pre-Scientists. Letters to a
mm,
Pre-Scientist. So you write to middle school kids. They are, who are socio-economically disadvantaged, and that will be very
mm,
rewarding. It
mm,
really was actually communicating. So we
mm,
were assigned, every scientist gets assigned one kid. So I was assigned a
mm,
5-year-old
mm,
girl, sorry, a girl in fifth grade,
mm.
and that was actually very rewarding. That correspondence and
Wonderful.
her curiosity and seeing that I was, maybe inspiring her and all that. But I also I felt
This was
more.
in US?
This
This was
was
in
in Canada.
US
In
or
Canada,
in
the second
Canada?
post.
Canada,
Yeah, the
Canada.
girl was in the US. She was in Ohio.
Mm,
Um,
mm,
but um, but I definitely wanted to reach out even more, and I
mm,
felt
mm,
I always feel most at home in the print medium.
mm,
So I was looking for outlets to write at and all that.
mm,
I wrote an article. I pitched a few, and I wrote one
mm,
in a place called Massive Science and all that. But the thing
mm.
was, really as a postdoc, you don't get much bandwidth and time. That's the
Yeah,
reality of
yeah,
it
you're right.
anyway. Yeah.
Yeah, yeah, yeah.
So I'd been wanting to do it. I just couldn't do it. And in fact,
Mm,
when I was, when it looked like I was not going to do physics as a career, my second best option that I was very seriously considering was science communication.
Mm.
Um, so that was there. On the other hand, at the same time, I also enjoyed giving talks. That was one of the most pleasurable
Mm.
aspects of finishing projects
Yeah,
for me,
yeah,
to have to go and give talks,
absolutely.
because I love explaining physics as much as I
Exactly.
could.
Yeah,
So, and when I learn something, I always have an imaginary audience in my mind that I'm explaining things to. And
absolutely.
all.
No, in
So,
fact, that's a great way of thinking.
yes, I
That's
think
actually one
so.
of the most effective ways of
I
thinking.
I absolutely think so. Yeah, that absolutely
Yeah,
gets you to the most fruitful confusions that give you clarity later on.
absolutely.
Absolutely, absolutely.
Yeah, true.
Um, so, and when I became faculty, definitely I felt like my wings were spread a lot more, and
Mm.
that this now can definitely be done. So around the time I was becoming faculty, or around the
Mm.
end of my postdoc, and around the time I became faculty and later, that is when I started getting more into Twitter as well. And
Mm. Mm.
I was seeing that on Twitter people were making very nice physics threads,
Mm.
and I knew a lot of very interesting physics things. So why don't I also make
Exactly.
threads?
Why didn't? Absolutely.
And
Absolutely.
these things had their own following, and I was very heartened by that, very encouraging.
Mm. 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 Mm.
So I was doing that as well. And at the same time, I myself wanted to approach some newspaper or magazine and ask
Yeah.
them,
Yeah.
can I
Yeah.
can I pitch something?
Mm.
But as a windfall, what had happened was, because of my physics threads on Twitter,
Mm. Mm. Mm.
the deputy editor of the science section of the Hindu,
Mm.
V. Mukundan,
Mm.
he
Mm.
wrote to me and was like, I've been seeing your threads. And flat out, he said, I'm making you an offer to write to the Hindu on matters of your
Oh,
interest.
wonderful. Wonderful.
So that was a big thrill. Um, and of
Fantastic.
course, I
Fantastic.
accepted. And
Mm.
since then, I've been writing essays on
Mm.
different aspects of particle physics that I thought were
Mm.
not really touched upon by other popular writers. Uh,
Popular types. Yeah.
yeah. So some subtle
Wonderful.
aspects of particle physics and cosmology as well, that I thought this is something the public should know.
Sure.
Um, yeah,
Yeah.
the thinking
But
public
but
should.
but important thing, very important thing. In fact, that is something which is very good about you and also Nirmalya, whom
Yes,
I've spoken in the past, is that you guys not only write to those platforms, but you also make the content open source.
oh
you know,
yes, yes,
yeah, that is something which I strongly encourage everybody to do that, because
absolutely.
some of the times these very outstanding things what you folks write is made paywall, is kind of
It is behind a
behind the
paywall. That
paywall.
is, yes, yes,
Yeah,
yes,
of course there can be some kind of opening at later stage and things like that, but
yes,
that is one of the very good things what you guys do. In fact,
indeed.
that's an excellent initiative, I should mention, because
Yeah,
the articles which appear there are of very high quality, but if it doesn't reach out to a very broad audience, and that would be a
exactly,
shame,
exactly.
isn't
After
it?
all, writing like this is, I mean, the spirit of it is for the widest outreach possible. And so
Absolutely.
this is the bit that we could do to get it done. Actually, I
Yeah,
was
yeah,
inspired by Nirmalya to do this. I saw Nirmalya posting
yeah.
this. And yeah, I
Yes,
was also
yes.
told that it is when the editor shares a PDF with us, and it is legal.
Yeah.
It is totally legal for us to share it. So
Oh, okay.
yeah, so
Wonderful.
that's yeah. So
Excellent. Yeah, as long as that freedom is given, that's important. That's
exactly.
very critical. Because
Yeah.
I have been critical about, especially the general media not being open for science. See, I can understand
Yes.
if they paywall things related to, let's say, political aspects or some even very nuanced discussion. But things
Yes.
like this should absolutely be made open source,
I'm
because
200% with you. Yes.
yeah,
Yeah.
yeah,
Yeah.
yeah, that would be good.
Yeah. That
No,
line,
I
somebody
really
has to
appreciate.
make the decision and draw that line. They have to
Yeah,
gerrymander that line a bit correctly. Absolutely.
absolutely.
Yeah.
Yeah,
Yeah.
yeah, absolutely. Wonderful, wonderful. See, it is so heartening to know, Nirmal, that you actually have been taking these initiatives. And the last part is that article
Oh
on
yes.
the
Oh,
Greek
oh
letters.
that. Okay. 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 So okay. So so last year I went crazy about Greek mythology. So I
Mm,
started reading. I started and finished reading books by Stephen Fry. He has a trilogy now
mm,
on
mm,
Greek mythology.
mm,
Very, very
mm,
fascinated by it for multiple reasons. And and then I realized, well, there's so many particle experiments that are named after Greek mythology. We know this: Atlas and
mm,
Zeus, Hera,
mm,
and so on. So, so and then I wondered, why did they name it that way? Some of them on their websites,
mm,
they do write the Greek mythological
mm,
funda behind it. And then I
mm,
started collecting these names
mm,
because I wanted to see how many experiments actually are there. So
mm,
um, I had, so among other things, I started collecting Greek mythology books as well. So I had an encyclopedia of Greek
mm,
mythology by Bernard Elslin.
mm,
And
mm,
whenever I had free time, basically I was just Googling these names in
mm.
a particle physics
Ah,
contest, the Greek mythology
nice.
names, and seeing if there was an experiment on that. And I was
Nice.
collecting a
Nice.
lot of experiments that I didn't know about. So this way, I was also learning physics
Mm,
actually.
nice. Nice.
so, so then I realized, wait, there might be only one person in the world now who is
Mm.
utterly fascinated by particle physics and who knows who's utterly fascinated by Greek mythology and has an almost encyclopedic knowledge of Greek mythology.
Uh.
And that person just has to write this article. So what I
Nice.
did was, I basically, that article that you mentioned, the
Mm.
names of
Yeah.
Greek
Yeah.
names from Greek mythology in fundamental physics.
Yeah.
That article, which is on archive now, is basically a
Yeah.
retelling of Greek mythology. Actually, I'm not explaining the physics.
Mm.
So this is
Nice.
my version of, here I'm actually playing the part of a mythographer. I've written
Mm.
the entire timeline of Greek mythology from the starting of the universe until the end of the Trojan War and other things,
Mm.
Midas touch and all that.
Mm. Mm.
So I wrote it in, because I also like to write other things. So I wrote the Greek mythology, but when I introduce names in the Greek mythology, I give links to the
Then
particle
you.
physics experiment.
Nice. Nice.
This is also
Excellent.
to show that almost all the major names have been taken by not particle physics, fundamental physics, astrophysics and
Fundamental.
cosmology
Yeah.
and particle physics.
Yes.
So
Yes.
almost all the names have been taken up. That was another point I wanted to convey, that you can tell the entire story of Greek mythology, entire
Sorry.
timeline across generations by using names from fundamental physics. So far I've
Fantastic.
collected
Fantastic.
115 names, I think. I have some more. I have to
Yes.
update that article. So
Update. Yeah.
it's
I'll
just
be
a
anyway linking
pet
that
project.
on the show
Okay.
notes. I'll be linking
Okay.
that
Okay.
paper on the show notes.
Indeed.
Interested
Indeed.
listeners would should actually go and check that.
Absolutely.
Very interesting
And
stuff.
there is, see, another interesting philosophical link between these two is that the quest of physics, especially theoretical physics and fundamental physics,
Mm.
and the quest of a lot of these Greek myths is to find explanations for weird things happening in nature.
Mm.
Like,
Mm.
for people back then, in I guess in the Mediterranean area, were very mystified by, why are these thunderbolts coming out of the sky? Why do
Mm.
diseases come
Mm.
and go? Why do these things happen? So for them, they personified everything. Oh, there is a guy sitting in the sky throwing
Mm.
thunderbolts, or somebody is shooting invisible arrows, poisoned arrows that come and give some random people
Mm.
diseases, and so on. Why do spider webs have this shape? There's a story for that. Now we know better. Now we attack these things scientifically. Nevertheless, it is that quest that is the starting point of science.
Science. Yeah. Yeah. Exactly.
So
A
that
lot of
that's the other
people.
connection. This is the reason why
Mm.
experimentalists, especially, name their experiments after the particular Greek mythological
Mm.
character or
Mm.
aspect of Greek mythology. So
Yeah. Yeah.
so that's the other
Very
connection.
fascinating.
That's why I put all this together in that document.
Very interesting. So, Animal, we are almost coming to the end of the conversation. Tell us a little bit about your future directions, because this is also as part of the series of Emergence. Uh, we would be actually interested in knowing about what you're going to do, not only now, but also your plans for future, because you are going to be visiting us on the Pratidhani multiple times
Absolutely.
over the course of time. So, tell us a little bit about your future plans and
Okay,
how
okay,
do you want to go forward,
right. Well,
both in terms
so
of your research and the outreach. Yeah.
okay, okay, absolutely. Okay, so what I hope to do is, in research, I want to actually step a lot more into cosmology.
Mm.
Um, that's again because that's been always another big fascination of mine. I have used cosmology in the service of particle physics before, but I want to attack cosmology for itself as well, both the theoretical aspects of it and the phenomenological aspects of it. So this may take a few years, but that's something I definitely want to do a lot more going forward. Um, and I want to spread the net of dark matter even wider. So I have been the story of my career has been spreading that net wider and wider. But now I want to spread it even wider. I've not really done projects on this ultralight dark matter and so on. Um, so those things I definitely want to explore a lot more. And again, in the next few years, I do want to step a little bit out of dark matter itself, actually, and think about other very deep problems in particle physics, such as where did even the baryons come from? As opposed, there's a big asymmetry between baryons and antibaryons in the universe, and nobody knows really
Antibody.
why. So mechanisms for generating this asymmetry. Um, and some peculiarities in the masses and flavor mixings in the standard model. Things like these have always bothered me. Now I feel like I finally have that freedom and scope to delve deeper into these deep theoretical problems. So that is on the research side. On the outreach side, um, so the Hindu is great, and I do see myself writing for them. But like any outlet, it has its own restrictions. For instance, external writers like us, we are given 950 words, and not much scope for pictures. And the Hindu has also the Hindu has its own audience, a
Yeah, yeah.
certain a certain bent of mind, if you want to say that. But I also want to write for other outlets, more research oriented outlets, also less research oriented outlets. Um, Something like Quantum Magazine. Uh, there is an equivalent
Wonderful. Wonderful.
of it in India. I forget its name, but things like that, The Wire and so on.
Mm,
So
mm,
I want to do that in print, but I also want
mm,
to. So print is where I'm most home at, but I
mm,
want to get out of home once in a while. And
mm.
um, one thing I would really like to do is to collaborate with the planetarium here,
Yes. Yeah.
the
Yeah.
Birla Planetarium, not the, so the
Mm.
Nehru Planetarium.
Nehru Pal.
Yeah, yeah, because they are doing some fantastic outreach as far as I
That
can
is.
see.
Yeah.
And Parmeshwaran Ajit, who's a faculty at
Mm,
ICTS,
mm,
right? So he's been doing some collaborations with them already,
mm,
and
mm,
the results are spectacular. He's been a
mm,
consultant on one of their movies. Very amazing work there. So I want to ask them, what can I do? Um, so either as a consultant or getting some hands-on work done, or they have these um, REAP students, REAP students.
REAP. Yes.
Yeah,
Yes.
so
Yeah.
those
Yeah.
projects, what can I do for those? How can I come and train those students? That kind of thing I want to get into. Um, One other thing that's very close to my heart, I'm not sure if this is outreach or the real job, is
Mm,
I discovered that IAC has a center for continuing studies.
mm, mm,
Really, and my eyes popped out when I saw that, because I didn't think these things were in India. Actually, I had seen
yeah.
this.
Yeah. It's been there for a very long time. It's been there for a very
Okay,
long time.
okay, it's been
Even
continuing.
when I was a student,
Uh-huh.
even when I was a student in Bangalore, I have seen
Okay,
that particular
okay,
center. Yeah.
yeah. See, that is something I have been wanting to do that. I have been seeing. I know how this works in the US and all that.
Mm, mm.
But yeah, I do want to reach out, or I want to teach something to
Nice, nice.
seniors also,
Mm, mm,
because to me, there is nothing sadder than wanting to have done something in your youth
mm.
and missing the train because got
Mm.
real life got in the way.
Yeah, yeah.
But you get a second chance to learn these things. That is what, at least in my mind, this is why older people come to learn the subjects that they missed in their youth. So that is something I really want to see what I can do about. I want to approach them and talk to them. So yeah, these are
Wonderful,
my
wonderful.
these are on my horizon.
Wish you very best for all the ventures, Nirmal. In fact, it's been a pleasure talking to you. Actually,
My pleasure as well.
Uh,
Thank you so
yeah,
much for the platform.
yeah. Yeah. We'll actually do this as I mentioned, because this is part of the emergent series. So as I mentioned, this is a series where we're going to actually continue to talk to people who are going to be coming on this particular sub kind of part of the Pratidwani series. And
Totally,
so
totally.
this
I'm
is
very, very looking forward to it. And of course, more interactions in between as well.
yeah,
Yes.
of course, yeah.
Yeah.
So this is Pratidwani, where we try to humanize science, and this time with Nirmal Raj.
Thank you so much.